Okay, and
start sharing my screen.
I'd like to welcome our speaker and our participants to today's seminar. It is my great pleasure to introduce Walaa Moursi from the University of Waterloo. So Walaa received her PhD in mathematics in December 2016 from the University of British Columbia under the supervision of Heinz Pauschke and Warren Hare. So Walaa, she was on a research fellowship at the Simons Institute, University of Berkeley, and she was after that postdoc researcher at Stanford University. And a couple of years ago, not very sure about the starting date, she moved to University of Waterloo, okay, where she is now with her kids. And of course, Walaa is working on great topics in the fields of monotone operators, convex analysis. She has a series of very nice papers in very good journals. So one of the worldwide experts on the Douglas-Rachford algorithm. So Walaa, thank you for accepting our invitation. You have 45 minutes for a talk.
Thank you so much, Adu, for the invitation. First thing, I start by thanking the organizers for this wonderful seminar series, and of course for inviting me. So, danke Radu, toda shuham, and bedankt Matthias. I'll jump into the problem right away, and then I'll cast back and look at the setting and everything. So let's look at the convex optimization problem. I want to minimize the sum of f plus g. So I want to find an x that minimizes this sum. And once we look at f plus g, this is very tempting to think about splitting methods. For example, Douglas-Rachford and other methods as well, depending on the assumptions on the functions, but Douglas-Rachford is the most robust because it requires just the convexity, besides some other assumptions like some CQs and accessibility to process. Now, the green problem of finding the x is not our problem. Our problem is, what if such an x does not exist? What if this problem does not have a solution? So here is an example. We minimize the sum of the quadratic plus this linear function. And this is convex when we assume f is positive semi-definite. And because we are convex, Fermat's theorem, together with the smoothness of the function, yields that this is equivalent to solving this linear system of equations. Now, it could happen that the system is inconsistent in the case when b is not in the range of m. And this is where we have a problem. So this is where our red problem starts. So let's step back to our setting. I gave an example in Rn, but we will be working in a real Hilbert space. So that covers Rn, Sn, but you could also allow little L2. And I will again be more general and talk about monotone operators and not necessarily the gradients or subdifferentials of convex functions. So let's start by recalling the definition of a monotone operator. That could be a set-valued operator, and it's monotone when you take 2 points in the graph and look at this inner product and you get something non-negative. This is a class of operator that generalizes the gradients of convex functions, or even more generally, the subdifferential of convex functions. But it could also include operators that fail to be subdifferentials. And the easiest example to think of is the rotator in the plane by pi virtue. So in view of monotone operators, we can write our problems more generally as solving this monotone inclusion. So I look for an x in X such that this monotone inclusion has a root, which is X. And the method that we are going to use is the Douglas-Rachford method. This method works by iterating or recursively applying the so-called splitting operator, which is defined in terms of the reflected resolvents of A and B by this definition. So, as I said, this is just a more general framework for the optimization problem that we care about. Functions f plus g If we are in the smooth setting, then by Fermat, we look at a root of the gradient of the sum, which is the sum of the gradients. If we go more generally and do not necessarily assume that we are smooth, then we actually look at solving this monotony inclusion. And here you need to be a bit careful. You need some CQs to get from here to here, unlike the case of the gradient. But again, let's assume that this is true. So we want to solve this monotony inclusion. The reason this is of interest is that you can use it to model many optimization settings. So if you want to minimize a function over a convex set here, then you can write it as minimizing the sum of two functions. One of them would be the indicator function of the constraint set. And it's clear from the definition of the indicator function that if a point dares to stay outside the constraint set, then it will be dead as a candidate for a solution, because definitely the indicator will make the overall value plus infinity, so we will never consider it. You could be more specific and make your objective function another indicator, in which case you're minimizing sum of two indicators, which is exactly modeling this convex feasibility problem. So if the green problem is fine and doesn't have a problem, then assuming that the monotony inclusion has a solution, classically, it's proven that if you start at an x0 and construct the sequence xn by recursively applying t, so you define your sequence xn, the governing sequence, it will converge weakly to a fixed point of t. This does not necessarily get you to the solution of your monotony inclusion, but there's a very nice bridge and in fact a characterization of the solutions of the monotony inclusion through the fixed point set by hitting it by the resolvent of A. And if you say finite dimensions, you can stop here and guarantee that this green sequence will get you to a solution of the monotony inclusion. If you assume that X is not necessarily finite dimensional, then you need a little bit of more work, fun analysis, but still the shadows will in this case converge weakly to a desired solution. So everything here will have a function counterpart, assuming that we have a critical point, then what we call the governing sequence will converge to a fixed point of t weakly. And you need to hit this with, in this case, the resolvent would become the prox operator of f. You need to hit it with the prox operator to get to a point in the set of minimizers of f plus g. So just to show you a flavor of what the resolvent, reflectors, resolvent, prox operator, all that are and how the method works, here is an example. We want here to solve the problem of minimizing f plus g. F and g are two indicator functions of these two lines, the blue line, the red line. And I want to find the point in the intersection, which is namely here. So I draw two lines in R3, but I stayed in the XY plane for the two lines. And here's how the method works. I start at an x0. And as I said, the way I construct the sequence, I apply t recursively. So you start at x0 and you apply t for the first iteration to get, this is your x1. And now you apply t again to this point to get your second iteration, and so on and so on and so on. So you get this red sequence that will keep spiraling. And I started x0 in a plane that's not the xy plane, and it's proven. It's a fact that if you start in not in the xy plane in this particular situation, then you will actually stay in that plane here. So you will never converge to that point in the intersection. And therefore you can see here that we really need the shadow sequence that you will get you there. The shadow sequence is the blue one that would get you to the intersection, but actually in an interesting non-monotonic fashion. And just to show you what the T looks like in this case, so that is actually what we called RA, and that's what we called RB. So in this case, this is just the reflector through the line. PU is the orthogonal projection, and when we take 2 times projection minus identity, you just the reflection through the line. So you apply a reflection through the first line, then a reflection through the second line, and then you average with the starting point. So this is how T operates. So assuming that we have a critical point, then we can take this, and everything is fine. But our red problem starts when we don't have a critical point. This is where things start going wrong, and this is where we start worrying, what would the method do? And here's what happens when I do something bad and start tilting the lines that originally were intersecting, doing well. I now tilted the lines, so they no longer intersect. There is a gap between the lines, and this gap is what we will call now this vector V. So I zoomed here. The lines no longer intersect, and that governing sequence that seemed to do nicely in the intersecting case, in the consistent case, is actually terribly behaving. And from fixed point theory, because in this case we don't have a fixed point, we can easily grab a result from fixed point theory that tells us that it will diverge to infinity in norm. However, something interesting really happens, and this is back to a result in 2003 by Bashka, Convex, and Luke. The shadow sequence in this case stays bounded, and even better, which I'm going to comment on later. So that was an example where the red problem occurs. And we start thinking, okay, we have a problem that has a problem, and we need to do something with that. We need to think, okay, the problem doesn't have a solution and we can't bring one out of the blue. So we need to do something about it. And we start thinking, okay, maybe we perturb the problem and get closer to another problem that is more promising than the problematic one. And the first thing that came to my mind is called, of course, perturbing it. But the question is, what would be the perturbation and how would we introduce it to the problem? And one obvious candidate for the perturbation, just because of the correspondence between the fixed points of the splitting operator T and the existence of zero, is the minimal norm element in the range or the closure of the range of the displacement operator T. The fact that T has a fixed point means that zero is in this range. And the fact that it doesn't have a fixed point means this vector V, it may be not at 0, but not at 10, in which case it will still be 0, but this is a problematic case that we will avoid, as you shall see later. But in general, this V could be non-zero, in which case we are actually in the case where the problem has a problem. So we define our gap vector V, and using that gap vector, we start perturbing our problem. And again, it takes us few trials and experimenting to see what would be the right way to perturb, but we ended up perturbing the original problem by looking at the graphs of A and B and perturbing one graph vertically and the other horizontally. So we introduced a vertical perturbation to one operator and the horizontal perturbation to the other operator. And we call this our normal problem, the problem of finding a zero of this new perturbed problem. And the generalized solution set is what we called normal solution. And it's exactly the solutions of this new perturbed monotone inclusion. We were actually motivated by the normal problem from linear algebra, or the normal equations from linear algebra. So the story has roots in linear algebra. So suppose that we start with an n by n matrix whose positive semi-definite, so whose symmetric part is positive semi-definite. That's equivalent in this case to saying that A is maximally monotone. And we look at this linear system of equations. We can rewrite this as AX minus B equals 0. And you can call this B. So B is BX for all X, BX is minus B, in which case we can look at this as finding a zero sum of A plus B. And similar to what I talked about earlier, if B is not in the range of A, then we have a problem, the red problem. And we start calculating the minimal displacement vector, which in this case, we found that it's actually the projection of minus B onto the orthogonal complement of the range of A. And in this case, the normal solutions that we just talked about here are the least square solution. So that was kind of like promising that we are at least recovering something that's known. So we might be on the right track. Okay, so I'll now go to, we looked at a static framework, it looked promising, fine, but what we care about is the performance of the method, the algorithm. So I'll now actually go through some of the history of dynamics from a fixed point theory of view, and also from the specific angle of Douglas-Rachford. So starting at x is 0, and when the monotone inclusion has no solution, which is equivalent to t being fixed point free, in this case, we know from fixed point theory that iterating t would yield a terrible governing sequence that would diverge to infinity and norm. However, if we assume that that vector v, which by definition is always here, but we will also assume an extra assumption that it is attained in the range and not just in the closure, then we have some nice results. So the first promising result, which actually motivated most of this work at the beginning, is for the case of two indicator functions, when we look at the convex feasibility problem. And when the sets do not intersect, T would still have this behavior, but the shadow sequence will remain bounded, and the weak cluster points are actually normal solutions. Later on in 2015, we were able to provide the first proof of convergence for the case of two affine subspaces, not necessarily intersecting, but in this case, we actually get even strong convergence with identified limit and linear rate. And then in 2015 and 2016, we made progress and we completely finished the story for convex feasibility problem, and we proved the full weak convergence of the shadow sequence in this case. But it wasn't until 2019 where we were able to make progress outside the convex feasibility. And the reason is, in convex feasibility, the geometry is so nice. And this is what we realized in the very latest work that I'm going to report on today, because convex feasibility was easier to deal with, but unfortunately, there was a major drawback that it hid a lot of things because we get them for free. We don't think about them as conditions. So in 2019, we were able to make progress in the setting of minimizing a convex function subject to an affine constraint. And in that paper, we needed to make this assumption, which appeared to us by that time as a good sufficient condition. However, we realized later, and this is what I'm going to talk about today, it is also a necessary condition to prove the convergence of the shells. And again, the progress we made here, I would say that as much as it was fun, it was a bit misleading, because even in the third case where we had a function subject to an affine constraint, the affine or linear constraints are actually very misleading because there is a nice geometry going on, but it hides a lot of things. So here's an example of the convex feasibility case.
Well, I have a question.
Sure.
Is there a meaningful formulation for this problem when the operators are both subdifferentials of, let's say, convex functions, not necessarily indicator and convex function?
Yeah, Matt, this is what I'm going to talk about today for two functions.
Okay, sorry.
So this is the results today.
Okay, very good.
Okay.
Thank you. Very good.
You're welcome. So that's why I said like there was a lot of difficulties, because these things actually, like with indicators, the geometry is nice, but you don't see much. Here the convex feasibility example. So we start at an x here and we apply t recursively. We get this governing sequence. It will not diverge to infinity and norm. And for this particular example in R2, we can show that the shadows will converge even in 3 steps. So here's an example where we can see that the shadows will get us to a best approximation solution. Related works to this, I would say that this formulation for the range of the displacement map identity minus t is of crucial importance. And built on that, we were able to actually get a lot of results. In 2017 and 2018, Lin and Yin proposed a method based on Douglas-Rachford, which identifies situation of infeasible, unbounded, and pathological conic/convex optimization problems. Later on in 2018, Banyak, Ballard, Stellato, and Boyd showed that for certain classes of ADMM, of convex optimization problem, EDMM can detect primal and dual infeasibility, and that used actually the minimal displacement vector. And in 2020, Banyak and Legris and Banyak provided very nice results where they extended geometric properties of the minimal displacement vector that we had for the case of convex function subject to linear constraint. So I come now to Radu's question. Start an X node, and we want to know what the behavior looks like. So the first thing is like Radu's question, can we learn more when A and B are nice, maximally monotone operator? When I say nice, because there is class that we need actually to throw away. So at least we have to restrict ourselves to the class that contains subdifferentials as subset. You don't need to worry about its definition, but we will be restricted to a class of nice operator that at least will exclude the skew operators. Now, first step is we're talking about the shadow sequence, which you are putting a lot of hope on. And the question is, can we characterize at least when it is bounded? So far in these works, the convex feasibility, we get boundedness for free, and outside convex feasibility, we needed a sufficient condition. Can we get a necessary? Now, suppose we were lucky and proved that the shadows are bounded, can we locate the cluster points? And if we can locate the cluster points, the story is like we get more greedy and we want to prove the full convergence. So I'll start putting assumptions. And I know that I, on the first slide, said I'm going to tell the complete stories. So now I'm putting assumptions, but I will convince you that that does not violate my claim that it is a complete story. So the first assumption is I'm going to assume that this holds true. A few slides ago, I said that we proved it. We proved it in finite dimensions when A and B are nice. Nice here includes subdifferentials. So as long as we are dealing with subdifferentials in finite dimension, this is always true. So we don't even need to assume it. Now, assuming A1, there is a beautiful geometry going on with those baby vectors, VD and VR. So I'm going to define two baby vectors, VD and VR. This comes from the domains set, and this comes from the ranges set. And using a fact, again, by Bauschka, Combet, and Luke, we can prove that VD is located in the polar of two recession cones, and same for VR. You don't need to remember what the cones are, but just remember that in the polars of some cones, and then we are going to locate them also in other polars, and altogether will give us some nice information about these two vectors. So that was the first location. Then now we are going to locate each of these two vectors in another two cones. And the way we do that is we're going to show that this inclusion is true. Once you buy the blue inclusion, everything is actually cheap, like it's that cheap consequence by applying this to B or to A inverse. So how do we prove the blue inclusion? Snapshot, I'll start by looking at this green set here. And this is always a subset from this. And now the beautiful Brazil rule kicks in. And it gets us as this is the same as the closure of the range of A plus the normal cone of closure of domain A. But this operator is just A. And now if you follow the green inclusion, you learn that the range of A is actually, so you learn that this set is actually subset from the recession of closure range A. So we get this first inclusion. Now, this time I'm going to use another classical result by Zarantanello, and that result gets us to this set here in red, and it proves that it's exactly this set. So if we combine these two inclusions together, we verify this inclusion. So because of the previous slide, we now have two supersets for those two. So we can locate VD in 4 different places, and there is polar cones floating around. We can use that and choose the right sets, and we can prove that actually the baby vectors that they talked about are actually orthogonal. And because of the definition of V and how VD and VR are, again, geometry kicks in, and we prove that V can be decomposed into the sum of those two beautifully orthogonal vectors. So I have to say that this result was actually first proven for the case of like when V comes from the problem of minimizing convex functions subject to affine constraints, so that the V there, Banyak proved it for two functions, and then we now prove it for maximally monotone operators. And then we have beautiful dynamic consequences for this. So this is classical from fixed point theory, very beautiful limit. And then these two, and I'm going here backward, there is nothing new here. I just used this limit and I dropped to the definition of T, and identity minus T can be written like that or equivalently like that. So this is what I plugged in here. So nothing new. But what's really new and beautiful is this limit now can be further refined into two limits. So if you look at this, this is just the difference between two consecutive terms in the primal shadows, and this is the same for dual shadows. And you can see immediately, first of all, just because of the definition of the resolvent, and this limit, you can see that you can recover this one from adding these two. And even more beautifully, now we get the necessary condition for the primal shadows when it is asymptotically regular. Let's see, if and only if this VR is 0, and we get a dual counterpart for this. So now we start having a condition when the sequence, the necessary condition when the shadow sequence is conversion. So remember, there is a condition that I talked about earlier that I say it was actually sufficient to prove convergence, and that was exactly this condition. And now we see how crucial it is. And now I need to put another assumption. And again, trust me, I'm going to convince you that this is not just put for that for no reason. I will convince you why this one is really important, but I'm going to talk about that later. So this time V is actually always by definition here, but I'm going to assume attainment. So I'm going to assume that V is attained. And that's equivalent to saying that Z has a solution. So the generalized solution set. And again, I'm going to convince you why we need this assumption, but intuitively speaking, what happened is that we have a problem that had a problem, and we come up with the new perturbed problem to solve what is going on. So if the new perturbed problem does not have a solution, then we are actually in a very bad shape. So this assumption is, in some sense, like really needed, but I will show you in a more rigorous way why this assumption is crucial. And even without getting to the end of the talk where I can show you that, this assumption immediately gets us to seeing some sort of fair monotonicity, which is beautiful. Getting from a setting where we don't have fixed point and life is miserable to now we have some sort of fair monotonicity going on. So assuming that the operators are nice, forget about what I wrote here. This is true again for subdifferentials. This sequence is fair monotone with respect to some set. Z here is the primal normal solution, and this is the dual normal solutions. Don't worry about this. The most important thing is that once you see a sequence, and this is just a shift, so you can discard, this is now a bounded sequence. And now you can see a characterization when the shadows are bounded. So if we only care about the primal shadows, it's if and only if the VR is 0. And now you can see, so again, we were so happy to see this because this was the assumption that we put earlier. It wasn't clear, like linearity hid it a lot. It wasn't clear what was going on. We just found that it will help us to get to there because of the geometry of the V vector and will be absorbed in the shadow, in the projection, everything. But now we see things clearly. VR has to be 0. We don't have choices. And everything has a dual counterpart. So now I'm going to drop to optimization setting. Monotone operators will stop there. We really need to get to optimization settings to make further progress here. So now f and g are convex, lower semi-continuous proper, and the operators here will be subdifferentials. And I'm going to put my last standing assumption that VR is 0. And I hope that if I was able to do a reasonable job and make you follow me, you know why I need VR to be 0, the necessary sufficient condition, we don't have options. Otherwise, the shadow would be not bounded, not even bounded. So because VR is 0 and V is the sum of these two vectors, we end up that V is actually VD. And I'm going to make an abbreviation so for the sake of readability. So instead of saying prox F star, I'll just write PF star for the proxes and the reflected prox. And that would be the DR operator when we drop from general resolvents to prox operators. And we have convergence in 4 steps on a slide. So the way we see the convergence of the shadows is in the first step, we are going to refine the definition of Z. And that would use the fact that, or the assumption that VR is 0. And that would actually get us from here to the new, so the original Z has a minus V floating here. It will now dissolve, and we will see that on the next slide. Now, once we refine the definition of Z, we put it on the side. The shadows are bound. Here, I don't want to do anything with this particular setting because we just talked about the boundedness of shadows under the assumption VR equals 0 for monotone operators. So we get that for free. And now we have a bounded sequence. We start looking at its weak cluster points. So we will show that the weak cluster points are actually minimizers of this sum. And now the full weak convergence will follow from combining these 2 steps. And again, I will go through a high-level proof for some of the pieces. But the first thing, we find the Z. So this is the original Z that we defined for the new perturbed problem. So we perturb one operator and the other vertically, horizontally, as I said. Now, magically, under this assumption, this V gets absorbed. Nice geometry is going on. And V is now further refined. So it will only be the zeros of this sum. Now, something really nice is going on here. We prove that, and this is true in general, if the set of critical points is non-empty, then it's exactly the set of minimizers. So we have a dichotomy here. We either have Z is empty or Z is the set of minimizers. And this is even new in the case of, in the classical case where V is 0. Now, the second step is the boundedness of the shadows. So this is something that we got for free. Remember, we had this fair monotone sequence. It's bounded. We block VR equals 0. We end up with this. So if you look at what happens here, that becomes a prox. And here, because VR is 0, we get this. So this component, you can discard the shift. This component must be bounded. It's in the product space bounded. So definitely this part is bounded. And now we have a bounded sequence. We can start talking about locating the weak cluster points. So this is a long theorem. I don't want to actually read the highly technical parts, so I'll focus on this and this. So the first one is the shadows. Let's call mu, or let's set mu to be the minimum of the integrable part of the perturbed problem, because we perturb the differential form. The primal shadows is bounded. We know this from the previous slide. What's really interesting is that we start actually now locating the cluster points. So the cluster points are the right ones. They do the right thing. They solve the normal problem. So they are minimizers of this sum. Now this part is actually right away from the definition of DR operators. So this is a second part. And anyone who is familiar with DR knows that we talk always about this sequence, and this one would follow immediately. Now, assuming that Z bar is a weak cluster point of the primal shadows, we also get value conversions, which is really nice. And these items are actually direct consequence. I have to say that step 3 in particular, the proof is actually highly non-trivial. I would say that it was a section in the paper. And now step 4. So again, item 1 is an important one. Item 2 is a direct consequence of 1. So once we prove item 1, item 2 will follow immediately. We have shown that the sequence is fair monotone with respect to Z times K. I forget about this part because this has a V and things in it, but fair monotonicity in the product space would still allow me to do something nice. So I take 2 weak cluster points, and because we just proved that under the assumption Z is non-empty, the argument is exactly the critical points, then both Z1 and Z2 are in Z, and therefore this is trivial. And now we use some of the properties of fair monotone sequences to conclude that this will also be in Z minus Z perp. And if you combine these two, immediately you will see that you have no choice but unique cluster point. And this finishes the story and proves the full weak convergence of the shadows. And I just need to now justify my claims. When I said I'm going to tell the complete story, I need to show you how critical the assumptions I put are. So the first assumption, this, as I said, it's always true when you work in finite dimensions with subdifferentials. So you don't need to put this assumption at all or even consider it. You can just grab the fact for free. And this is not a typo. I jumped to A3 first because it's easy to address on the same slide. So A3 is the one that when I talked about the VR to be 0, because again, if I actually didn't stress on it enough, but VR 0 is actually necessarily insufficient condition for the boundedness of the shadows. So that's the least we can assume. We need it to be bounded for sure. So this is, again, this is not overwhelming. And then I come to this assumption that V is attained in the range of identity minus T. And I remind you that V is the minimal norm element in this closure, but the attainment, it may or may not be attained. And I show you now that if A2 fails, we can't say much. We can't tell a lot. And I will show you 2 examples where V2 fails and the shadows does extremely well. And V2 fails, or A2, sorry, fails, and the shadows does extremely bad. So here is a positive example. I work on the real line and I want to minimize the minus of the square root subject to x equals 0. So clearly we have here the only minimizer is 0. So the argument is non-empty and it has 0, or it's in fact the singleton 0. Now let me verify that A1 and A3 are satisfied. A1 of course is satisfied. We are on the real line, finite dimension of course, and we work with subdifferentials. So A1 is satisfied. Now A3 is about VR being 0. And again, if you want to see what VR is the smallest norm element in this set. Now, this is a function with a bounded domain. Therefore, the subdifferential has the domain 0. Therefore, it's actually surjective. So the range of f is everything. The range of partial f is everything. And therefore, this set is everything. Therefore, VR is definitely 0 because you're taking the minimum norm element. So Z is empty because if you look at the sum of the subdifferential, it's actually empty. Their domains do not even meet. But the argument is not empty. And if you look at this set here, and we calculate what the V is, it's 0, but it's not attained. It can't be attained. Otherwise, if it's attained, Z would be non-empty. So here we are in a situation where A2 fails. But we also have a very special shadow. It takes everything, throws it into 0. So no matter how bad this, I don't even care about what it does, it will converge in one step. It does extremely well. So this is an example where the shadows does fantastic, no matter what the governing sequence does. Now, here is the negative example. So this time we need to work in R3, and we actually visited an example by Ryu, Liu, and Yin in their 2019 paper. So in R3, we take the ice cream cone, and our function would be minimizing a linear function plus the indicator of a subspace subject to the cone constraint. And now, because this is such a demanding example in work, so we need to be able to calculate something in closed form and detect the behavior, we will choose a special starting point. So we will start in the XY plane and then fill in a lot of details, but we can show that V is 0, but not attained. As I said, clearly A1 here is satisfied, and we can also verify that the A3 is verified, but because V is not attained, the critical points or the set of or the normal solutions is empty. The set of normal solutions is empty. The set of minimizers is actually non-empty. It's the intersection of the cone with this subspace. And because of this smart choice of the starting point, we can actually calculate the shadow sequence, and we can show that the shadow sequence in this case will diverge to infinity and all. So there are two scenarios where A2 fails, and we can't say much. So if A2 fails, it's actually inconclusive. We can't tell much. So that was the talk, and I have to say that there are tons of references. So I found that the most efficient thing is that you can just look at the paper and look at the references they're in, and that would be hopefully comprehensive enough than putting them on the slide. Thank you so much again, Badu and the organizers, and thanks everyone for attending.
Thank you very much, Walaa, for a very nice talk. Are there questions? Now, let me start. And yeah, I'd like to ask first, Walaa, to which extent can this approach be extended to, to different algorithms, or different algorithms, let's say?
I know.
Forward backward, for instance.
For what?
For forward backward algorithm.
I tell you what the problem is forward backward. We actually looked at this question. So forward backward, I have a paper on forward backward. Interestingly, the V is the same, and the normal problem is the same in the case of forward backward. That's fantastic. Now, if you look at the decomposition of V, in the case of forward backward, actually what you get is that VR is cannot be zero, because what happens in forward backward case, if VR, it can be zero, but in this case we are consistent. What happens in forward backward is that the domains one dom A minus dom B would always be everything in the classical setting of forward backward, because one operator is co-cohesive, so it's full domain. So the domain set would be everything. And what happens in this case, when you take the intersection, the range would be the range of the displacement map would be the intersection of the sum of the ranges of range A plus range B. This is where VR comes from. And if VR is zero, then this means that V is zero and we are consistent. And the other problem with forward backward is the following: you only have one sequence. What saves the day and makes Douglas-Rachford very special is the shadow. Forward backward is like the only sequence that you have is the one that has no fixed point in the absence of solutions, and it will always diverge. And even if you try to play the game of shadowing, the problem is that you're stuck, because the shadow, the gap vector in this case would behave terribly when you shadow, because of its location. In forward backward, for instance, when you shadow, the V is, for instance, I gave you example for the case of F is the indicator of a subspace U, and G is just a convex function. The shadows that you get in this case is projection onto U, T, and S, right? Yeah. And because of the location of V, it's actually a new perp. So you can write, and linearity, and I'm giving you a simple, like an example that I can talk about. So this gets absorbed automatically, and this is actually a bounded sequence, and we can say stuff starting from there. I mean, there's a lot of things that you can say. In the case of forward backward, even if you try to shadow because of V now, and because as I said, the VR is the one that we need to be zero cannot be zero, because that will bring us to the consistent case. So in this case, V would be actually in U. I mean, in this case, if you look at it, that would be, it is not in U perp anymore, and that won't get us anywhere. So forward backward, I don't know about it, but there is a potential, I think, for other like for variants of GR, like ADMM and stuff like that. And
but like for instance, I mean, this is a kind of very fancy subject, like for the lifted algorithms we have now in the literature, when like one wants to, let's say, get win one dimension. Yeah? I mean, there are some recent papers, actually, by Ernest Ryu some years ago, and then by Yura Malitsky and Metten. So they have some variants of some lifted algorithms, which are kind of related to Douglas-Rachford.
Yes.
So what about this kind of methods?
Well, I haven't looked into that, but I think it would be interested to look at it from that perspective. I mean, this is definitely a very natural and good question to start looking at. Okay. So, Xiaowei Chen. Do you have a question?
Hi, Walaa.
Hi, Xiaowei.
I have a question. say pages 28.
Okay, 28.
28. Yeah. We see the is related with V, but we see the result. The result doesn't but the result doesn't relate with V. That is, we maybe not unique, right?
Can you clarify your question, Joey, please?
Z is related with the vector V.
Z, yes, is related to the vector V. That's true.
But the result, are related with the V. That is for any V, such as for a new
no, it's
V.
not for any V. No, it's not for any V. It's that particular V that's like this needs the V that we are referring to is the minimal displacement vector. So this is the V that we are using, not any V. This is the one that we need. Yes. So the minimal norm element in the closure of range identity minus T.
And this is unique. I mean, there is no, this is a projection on a closed convex set. So there is, only one.
Yeah, this is a maximally monotone operator away. So this is a maximally monotone operator. So when you close up the range, you get non-empty closed convex set. So this is a well-defined vector.
Yes.
Okay.
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 Did that answer your question? I think Robert has a question.
Yes, Robert. So from the other office.
Hi, Robert.
Hi, Walaa.
Hi, Robert.
Thanks for the talk. Can you go back to the slide 32 where with the assumptions A1, A2, A3?
Yeah.
Okay, my question is about A1, namely, so okay, you say in finite dimensional spaces and for subdifferentials this is fulfilled. Are there situations when this is not fulfilled, or is this open?
Okay, so there are situations where it's not fulfilled even in finite dimensions when you have, like I gave you an example where even in finite dimension, this is not true. So if you take A, okay, let me write down, take A equals the rotator in the plane by pi over 2.
Okay.
E equals the rotator by minus E. They're both maximally monotone. That's the easiest way, right?
Yes.
So you can show that the right-hand side is R2.
Okay, we don't have to go into the details. So this
and this one is actually a singleton. Okay. This is what I wanted to say. So you can actually show like with the, I mean, it's everything is computable. So you can show that this is just 0. And you can show that this is the entire space. So this fails. That's why you need subdifferentials. Now, the other thing is comes to the finite versus infinite dimensional. This is not completely sorted out yet, but stay tuned because there is something coming out for that. But yes, this is, again, you can't work with general maximally monotone operators. You could always, you need to discard certain classes, definitely.
Okay, thanks.
Thank you. Other questions? So then let us stay with condition A. Okay, then A1. Then I mean, this is a very kind of particular setting. Yeah? I mean, are there some other situations when this statement?
Yeah, if A and B are 3-star monotone operators,
okay,
or if one is 3-star and full domain.
Yes.
So there are more general, and the paper had the more general situations, but I didn't want to drop into like defining 3-star and those guys.
Yeah. This is a nice class of operators.
Exactly, and that's why like the counter example actually features the guys that are outside this class. So you can see the Q operators give us a very beautiful counter example in R2.
Yes. Okay. Heinz.
Thank you, Walaa, for your very nice talk. And I would like to follow up on Radu's question on it. So the splitting methods you mentioned by Rio and by Malitsky and Tam, that's a really good challenge. I don't personally see at all right now how to do this, because the governing sequence there is much worse structure-wise than what we see for the governing sequence of monotone operators, where you have this beautiful firmly non-expansive operator, underlying monotone operators, and so on. So for the other two algorithms, you're much more at the boundary of that. You're not even firmly non-expansive. You have to under-relax to become average. So I don't see what's going on there. The second comment is, and this is something that Fran Aragon Artacho made me aware of, there's actually a third new splitting algorithm by Ruben Campoy, who is in the audience. I just wanted to point this out. Thank you.
But by Heinz, so I propose to, my impression was that Ernest called these algorithms lifted algorithms. Is this so you call the splitting or?
Yeah, I mean,
I don't know.
You try to generate.
What would be a good notion, since you also have a paper, a very recent paper on this topic?
Yeah, I love these algorithms. They're really, it's a nice, fresh idea, you know. Okay. And some of the experts are maybe in the audience. My question would be, if you are not frugal, so frugal. Can you get away with even less factors in the product space? That would be nice, you know. Of course, if you can reduce it by one, that's awesome. But could we do a further reduction by, say, throwing frugality out of the window if the operators are cheap?
Okay. Great.
Thank you.
Thank you. So Robert, is this an old raised hand? Or do you have another question? Okay.
No question.
No, okay, no other question. So are there other questions from the audience? Comments? Okay, suggestions. So then let us stop here. Walaa, thank you very much for a very nice talk.
For the invitation. Thank you.
For a very nice discussion. So we will post a video and the slides on our website. And I'd just like to announce that our next speaker will be Ernest Rio, who was mentioned several times today. So I want to wish you, we should close with the information, which is again sad news, but probably it's a good place to say it here. So I was told last week by Dieter Klate that on September 16, not only Asen Donchev, but also Andreas Grivang passed away. So on the same day, the two mathematicians, optimizers, passed away. So this is sad news, but I guess that this is a good place to announce also such news. So I want to wish you a nice week. All the best. See you next Monday.
Thank you. Bye.